I shouldn't have said anything. My headset wasn't connected, so I couldn't hear any reply. Good morning, Mina. How are you?
Good morning, Dr. T. Good, how are you?
Let's see. See here. Going to start my video. Okay. Let's see here. Okay. Good morning, Cindy.
Hello.
Hello, hello. It's my visible crowd.
Morning, Dr. Terrell.
Hey, Solomon. Good morning.
Morning.
You're part of my invisible crowd. I mean, I see your name.
Sure, just for today.
All right. Good morning, Diane. Let's see here. I should view my stupid. No, I don't know how to see it. Nope, that didn't do it. There we go. Okay. So Hmm. Well, I'm getting a little bit late here, but so I will go over and or post some more homework problems today. So if you want to think about ones you'd like to request me to do, I would be happy to work on them. They're, you know, they're actually easier than the chemistry ones that we've been doing, but they're still a little bit tricky. So I am most happy to go over them. I think I'm all done with all the homework, so I could probably help. All right, so last time we talked about PN junctions, or we talked about semiconductors at least, and we discussed how there can be P-type silicon and N-type silicon, and so there's a special thing that happens at the junction between those two materials, which is that there's a depletion region. So the holes from one side get into the electrons from the other side, and they annihilate. And so that depletion region also has an electric field, right? Because you'll recall that the when you make a P or an N-doped side, for example, to make the P-doped side, you make a fixed negative charge and a mobile hole. And so the fixed charge stays stuck, and then in the other side, the opposite fixed charge stays stuck. And then there's an electric field developed between the two. And so whenever you have a depletion region in a PN junction, you have this built-in electric field. And that actually creates a potential difference between the P and the N side, such that if you create electron hole pairs in that region, they're swept apart by that field. They, so there's one polarity of electric field, right? So the electrons head for the positive end, and the holes head for the negative end. And it's that charge separation that makes the PN junction work. So there's two ways that can operate. One is kind of three ways. One is photovoltaically, where if you create an electron hole pair in a PN junction, then the electron in the hole will be swept apart, and you'll get current and potential. Does that make sense, Casey?
So I don't know if Casey can even hear you. Her Wi-Fi is acting up today.
Oh, that's right. She's looking incredibly stoically, completely featureless. All right, Cindy, you're up. So you have an electric field, yeah?
Yes.
Yeah, so far so good. Good.
So far so good. Yeah.
So you have an electric, good. So you have an electric field. You create, And in that, within that field region, you create an electron hole pair, right?
Yes.
And so the electron will be attracted to the positive end, and the
Mhm.
hole will be attracted to the negative end, right? And
Right.
that means that once they're created, they're swept apart, which is a lovely little thing that nature did for us. Of all the symmetries and all the weirdness in nature, thank you, God. Thank you. You made
It makes our
photovoltaics
electronic
possible.
life, yeah, so it makes our electronic lives much easier.
It sure does. Oh my God. We would be in just steampunk hell otherwise. Right, Van?
Yes, sir.
Good. Good answer. Oh gosh. So one of the other things, I mean, apropos to what we're talking about now, is that if you have a depletion region and light strikes it, when the light is converted into these positive and negative charges, right? The energy from the light disappears and you get a positive and a negative charge. And that positive and negative charge is then swept apart by the electric field. And then you collect it and you amplify it, and there you've got a photocurrent. So, you know, and this is a rather sophisticated diagram, right? But it shows, you know, some sort of coding. Then there's a negative contact here, right? And negative contact, and then the N type, I guess that probably has a positive contact. But when the light comes in and it creates an electron hole pair in this region, the holes are swept up to this negative terminal, and the electrons are swept down here. And you basically you're measuring the current between this back plane and this front plane here. And you know, there's all kinds of different ways to configure this, but this is one of them.
I have
And
a question, Doctor.
yes, Van, yes.
Is it the thickness of the N dot and silicon dot matter?
Mm-hmm. Not really. No. The you know, there the P type, the P region here is thin, right? This is very thin. So the photons have to get through here, and they have to be created. Well, you know, I think they have to be created somewhere in this depletion region. So I don't know how they do it, but you can create very high collection efficiencies in these devices so that, you know, a quarter or a half of the photons that strike the surface are collected as electron hole pairs. And so I mean, it only collects light coming from this direction, you know, coming from the top. It can't collect light from the back. That's a good point. That might be a cool project to work on, right? A bidirectional light detector kind of thing.
Thank you.
Yes, you're welcome. So
That's
then,
be
you know,
Van's extra credit.
exactly. Just get me a Nobel Prize and I'll give you 10 points. So, anyways, there's just different band gaps, you know. And in order for a semiconductor light detector to work, the photon energy has to be greater than the band gap. So the band gap is the energy difference between the HOMO and the LUMO, or the valence and the conduction band. And, you know, so photons that have an energy less than this band gap generally pass right through. There's no way for them to interact, and so they don't. Interesting, huh? And then photons with an energy much greater than that band gap, they will also tend to pass through that material. But photons with energies that are approximately the same as the band gap or a little bit greater than the band gap, they will be absorbed. So in the UV and the vis, they use silicon. And then in the near infrared, you use InGas. Then in the infrared, you actually use HG, mercury doped cadmium telluride. And these are these are in the infrared. Lead sulfide is not a proper semiconductor, though. It's more of a bolometer. I think it just detects energy. Anyway, I'm not sure. So photodiodes can be made in arrays. This is probably a 20-year-old photodiode array. But the thing is that an array of photodiodes like this, there could be 512 or 1024 or 2048 or 4096 diodes in a line like this, and what happens is that they're all activated at once. And so if you have a spectrum that's falling on a photodiode, the photodiode's placed on the focal plane of your detector device, then you can collect the entire spectrum at once. And that integrating advantage is huge in the UV vis. And so you can get very fast UV vis instruments using array type detectors. And you tend only to be limited by the readout speed. And so if you can read these out, a microsecond per pixel, you might get the whole spectrum in 4 milliseconds, So in any case, these are pretty cool.
Excuse me.
And
Dr. T.
yes, sir.
I have a question. Could we do a couple homework problems, if that's possible? Or
Yes, we can.
Okay.
Yes, we can. Yes, we can. I mean, I don't really have so much of an agenda here.
Okay.
Let me just look ahead just a little bit.
Yeah, that's fine. You can.
And
finish
yeah,
that.
so
Okay.
I'll give me 10 minutes or so, and then we'll get into homework.
Yeah, that's
But during that time,
mm-hmm.
you need to think of some questions.
I have 4.
All right.
That's how I was waiting.
Okay. Well, you have 4 numbers, right?
Yeah. For example. Yeah.
Good. Okay. All right. Okay. Cool. Excellent. All right. So so if you have a photodiode array, basically that means you have along the focal plane of the instrument, you can have this diode array. This is kind of a weird example here because it doesn't really show how this is the focal plane. But it's basically these mirrors here are conjugates. So basically the same focal length on the elliptical mirror and the grating. And that means that, it'll place wavelengths at a sort of a linear array along this focal plane. And I don't really know how they work, but trust me on this. And so then you can read out the array, you know, and you got red, orange, yellow, green, blue, indigo, violet. Then, you know, ultraviolet's down here, infrared's out there, you know. And so they're very fast. But you notice, you know, they're inherently single beam instruments. So you put a sample in, or, you know, first you put in a blank and you record that spectrum, then you put in a sample and you record that spectrum, compute the transmittance, and then compute the absorbance. And there's another minor problem with these is that the entire sample is irradiated with all wavelengths at the same time. So if the entire sample is irradiated, then your specimen gets sunburned. Does that make sense? So it's always in the ultraviolet. There's always ultraviolet impinging on your sample. Have you ever had a sunburn, Van?
No, sir.
You've never had a sunburn?
No.
Oh my God.
Yes.
For real? Oh my gosh. I bet you Cindy's had sunburns. I bet you Casey's had sunburns. I mean, they're painful.
Yes.
You're just out in the sun and your face is all, you know, I mean, sometimes they can be just minor, right? But you know, if you have a single beam spectrometer of this type, they're getting UV irradiated constantly. And so it's an issue and you can get some degradation. So it's not really that good if you're going to be like doing a long-term study, because you can be breaking it down, you know. But you know, you can have a shutter there and turn it on and off. That's fine. But you know, you kind of have to be mindful of that. Okay. Photodiodes, monochromators, da, da, da. There's some advantages and disadvantages. So, you know, arrays are fast and they have no moving parts. You know, so this is an advantage of a diode array. On the other hand, you can vary the slits on other type of monochromators, and you can typically get a little bit better resolution. They're also larger. You know, that's another thing is the photodiode array instruments are typically fairly small. And so these are typical values, but they're not, you know, you can do better with the particular, you know, with a different design. So I guess I'm sort of couching this in kind of vague terms here, but photodiode arrays are fast, but monochromator designs are a little bit higher resolution. So 10th nanometer is higher resolution than 0.5 nanometer. You know, so this is higher resolution than this. And then stray light there's differences in the stray light that you collect. And I'm not really sure why that is, but yeah, I'll take Harris's word on that. All right, so all right, I'll talk about charge coupled devices, then we'll do problems. How's that? So the charge coupled device is typical of your camera on your phone, or the camera in your camera, or the camera, basically. So, and the way that they work is that you have In this case, you have p-type silicon, right? And then you have an insulating layer grown on top of that, right? It's real easy to grow SiO2 on silicon. You just put it in a furnace. So you can grow an impermeably thick layer of SiO2, and then you can place a contact on top of that SiO2. Here they show Si, but this also could be aluminum or copper or anything, right? Any conductor up here, right? And then you charge that up. Well, in this case, you have p-type silicon, right? And then in this region around the plus 10 volts, you're going to repel the positive charges because you've got plus 10, you've got p-type silicon here. So there'll be a depletion region around this capacitor. Then when light comes in and it creates electron hole pairs, the electrons will be sucked into that region and they will be stored at this SiO2 p-type silicon interface. So every photon adds an electron to the charge on this capacitor. So here's a capacitor. It's MIM, right? So it's like metallic, insulating, and then metallic, MIM, right? Now this side is special, right? It only becomes metallic after light falls on it and charges accumulate. So you got MIM, charges accumulate there for every photon. And then as this capacitor charges up, it charges in proportion to the amount of light that has struck the silicon here. Yes, good. And then what happens is you have this two-dimensional array of electrodes on the SiO2, and every point on that you can interrogate independently because you have this crossed array of electrodes, and you can move the charge around on the surface, so you can shift the charge around, and you can read it out on a destructive readout on one edge or one corner or something like that. So this turns out to be one of the most sensitive ways to detect light, and it creates an interesting way to look at the signal to noise qualities of light, right? And when you think about it, light is a quantum phenomenon, right? Because there is a single entity, that's the photon is all. That's how light comes. It doesn't come in smaller packets, right? And so you can count photons with a device like this, right? So, for example, here's on this graph, they have pixel number versus photon count, right? So this is, you might have the pixel number along the 384, and then the 576 is it's, you know, another direction. This could be like the vertical direction on the focal plane. And so a band of light here that's falling towards the middle, that can accumulate counts here in pixel number 125, right? So that might be around here. And so as you average more and more, you accumulate this spectrum here, right? So you can start to see if you average 500 scans together, right? Then you can, this peak will rise out of the background, and you'll start to see some smaller peaks as well. And so the type of noise that comes up in this way is called shot noise. And shot noise is proportional to the square root of the number of counts. So if we have, like, let's say that on average we have 1 count per pixel here in the times 1, right? Square root of 1 is 1. So the signal to noise ratio on this row is 1, let's say. So there's 1 additional count for every dark count. That would be a signal to noise ratio of 1. And then as we go up here, if we go to 5, now we're gonna count 5 times. And so now there will be 5 background counts, right? Well, to be honest, I'm not sure. The signal to noise improves as the square root of the time that you count. So square root of 5 here would be like 2 point something, right? 2.3 or something, right? So now this peak here has gone from 1 to 2.3. Then at 10, it'll be more like 3. And then 50, then at 100, the signal to noise ratio will be 10. So the noise floor here will be 10 counts, and the signal will be 100, say, for example, right? Then at 500, it'll be, you know, whatever the square root of 500 is, maybe, you know, 25 or so. $20 would be 400, yeah. So maybe 25. You'll have like, you'll have a large peak like this. And the signal to noise ratio on the peak of that will scale as the square root of this so-called multiplication here. All right, so I've sort of beaten this guy to death. And here you can see some statistics that compare photodiode arrays, photomultiplier tubes, and charge coupled devices, okay? Now, I just want to bring one thing to your mind, to your attention here, is that as the signal acquisition time increases from 1 to 10 to 100, the minimum detectable signal decreases, right? So you need, you know, 6,000, you know, whatever photons per second to detect a single photon. In 1 second, 600 in 10 seconds, and 100 in 100 seconds. And you'll see that these don't scale properly, right? 6,600, this should be 60, but it's about twice that. Then we got 30 and 6 instead of 30 and 3, and then 2 here. So this is not quite working out. But then with the CCD, we got 33 and 0.3. So these are very linear. So this is why the CCD is beloved in terms of light detection. But just one last point, CCD is basically the best light detector you can use in chemistry. But if you absolutely have to leverage everything for ultimate single photon detection, you got to use a photomultiplier tube. That's why down in Antarctica, do you guys know about the ice cube? So ice cube it's a cubic kilometer of ice. It's on the South Pole. And this cubic kilometer of ice has a bazillion PMTs in it. So they've drilled all this array of holes down a kilometer into the ice. And then they lower photomultiplier tubes into the ice. So they've got this three-dimensional array of photomultiplier tubes. And they use these to detect neutrinos. So neutrinos are these particles that are just constantly irradiating us, constantly. But they almost never interact. But when they do, they make a shower of particles. And so they monitor every single photomultiplier tube. And whenever there's an event, they look at the shower of particles that's produced. They get this three-dimensional view of the shower. And that is what, and that's how they can tell, oh, this was that a certain type of neutrino or something like that. So anyway, I'm not a physicist, but I did sleep at a Holiday Inn, so you have to listen. But but so that's when they want to go for the ultimate signal to noise ratio. All right. So I am ready, Solomon. Are you still there?
Yeah, I'm still here. I've been listening.
Oh, thank you so much. Thank you so much. Thank you so much. I admire you. I admire your tenacity.
Thank you. I'm trying to get an A.
So awesome. I love it. I love it. So what problem number would you like me to go over?
It's gonna be 13 and 14, and then 43 and 44. 43 and 44 was the last 10 slides you're talking about. So can we go over those two?
Sure. So 43 and 44 here. Let's see here. Okay, standard uncertainty, right?
Yes, those last two, yeah.
So I get it. Okay, great.
Can we do 31?
I have to log back in.
Can we do 31 also?
31?
Yes, please.
Well, I don't know. I only do questions for people whose name begins with S. And I'm sorry, Van, your name begins with V, so I have to do only what Solomon says because his name starts with S.
That's okay, Dr. T.
Okay, so which one? Oh no, she's too nice. She defeated me. Okay, so which one did you want me to do, Van?
43,
I
44.
say 31, 43, and 44, please.
Okay, 31, 43, and 44. Okay. All right. So 31 here is going to be, okay, 31, 43, and 44. Okay. All right. So let's look at this guy here. So so here is I mean, this is actually a little bit ahead of where we are in lecture, but it's perfect, right? Because this is the kind of nonsense I'm trying to talk about with signal to noise ratio. I know this all sounds like, what is he talking about? Is this chemistry or what? Damn it. You know, it's not. It's basically engineering. I don't know engineering. But thing is that, you know, like you can look at the uncertainty in a measurement and you can plot that uncertainty as a function of the time that you spend making the measurement. So for example, you know, up here, you know, you've got maybe an uncertainty of 1 unit, whatever that is, you know. And if you measure this just one time, measure the signal for 1 second, right? And then you wait a little while, then you do it again, right? You're going to find that the uncertainty is up here around 1, like it could be 1 part per million or something like that, right? If you only dedicate 1 second to the measurement. Now, if you dedicate a longer time to that measurement, you can increase the signal to noise ratio from 1. Well, you can decrease the noise to signal ratio. You can decrease it by an entire factor of 10, right? Along this line. So this is measuring for 1 second, and this is measuring for 100 seconds here. And you can see that this is 1/10 of this, right? And so there's this beautiful linear range here where the signal or the noise to signal ratio here, no, signal to noise ratio, no, noise to signal ratio, sorry, is improving as the square root of the signal averaging time, right? So the square root of 100 is 10, and 0.1 is 1/10 of 100, of 1, right? 0.1 is 1/10 of 1. So you go 100 times longer and you get 10 times better signal to noise, right? And this is what's referred to as the shot noise limit. And this is always a good sign if you can see this, right? However, when you start going to really long times, a lot of times you lose this advantage. And your signal to noise ratio will actually deteriorate. And that's what they've shown here. And there's a lot of, you know, points, one on top of the other. And they're kind of showing these trends up and down, right? And these are most likely like temperature changes in the room, right? Where you measure and then it's getting warmer, then it's getting cooler, then it's getting warmer, then it's getting cooler and warmer, you know. That's possible, you know. And it could be that there's actually literally a change in the amount of CO2, you know, or in the amount of CO in the atmosphere, you know. So what you gain in time, you gain with limited, there's always a limitation there. Because you want to, ideally you want to take a snapshot, right? You'd like to know at this point in time what is the CO concentration, right? And so after, if you collect for 300 seconds or 1,000 seconds, then you begin to lose that resolution. And so there's a beautiful range of times where you're measuring in what's called the shot noise limit, and the signal and the noise floor is dropping in proportion to the square root of the time, but then that is lost. So let's just see here. Holy cow. So standard uncertainty for 4 seconds, right? This would be, you would come up here, right? And you would go up here, and this would be like, so 3, 4, 5, 6, I think. I think this 4 seconds would be 6. Yeah. So this guy, let's see how I do. So this first one should be 6, right? Let's see what, that doesn't show you the answer. Oh, I got it wrong. Come on. You got to show me the answer here. Anyway, this would be 6 seconds, right? And then for 16 seconds, we'd go 10, 20, 30, right? So 20. And 16 would be like right around here. So this would be around 0.28 or something, 0.27, right? I'm not sure why this isn't showing us for. So in the standard uncertainty predicted for 100 seconds of signal averaging is 1/10 of that for 1, which is, this is about 0.12 or 1.2 to 0.12, right? I'm sorry, I'm botching this all up. And then why does it increase? Why does uncertainty increase averaging for 200 seconds or more? This is a drift. So let's check that answer. So I got that one right, and I don't know about the rest. Does that help? That wasn't so helpful, was it? So 4 seconds, let's see here. This is 0.6, right? And then for 16, it should be half of that, right? So going from 4 seconds to 16, that's a factor of 4 increase in the time. So square root of 4 is 2. So that should improve our noise by a factor of 2. Let's see if these are right. Yeah, these are both right. So in any case, what's next? That was 31, right? No, that was 43, right?
No, that was 44, doctor.
That was 40.
Oh,
Wait,
sorry,
on mine it says 43.
43, you're right.
That's 43,
Right.
43.
My bad.
44, I'm not actually sure how to do this yet. So why don't I answer this one on Thursday?
Oh, okay.
All right. If I could do that, yeah. So
Yeah, that's fine.
I'll go over that one on Thursday. All right.
Okay.
And then somebody wanted 31, is that right?
Yeah, Van wanted 31, I believe, or
Yeah.
35.
Yeah, 31 I think she wanted, right? So I'll show you how to do
Yes.
31. Okay. I worked on 31 for quite a while. It's like, damn, this stupid goddamn geometry bullshit, you know? And it was just a little bit complicated, you know? Because it depends on both the length and the width over the stupid thing, right? And so let's see here. Yeah, there we go. So I'll show you what I did here. For this guy, I'm going to jot down some of these values. 0.05 dB per centimeter, and I'll use the examples that I found there, if that's okay. So 'There we go. Wait, no, there we go. 31, 43, and 44. Okay, good. So here's question 31, right? And so I'll just show you what I've got here so I don't screw it up too badly. So basically, they tell you the loss coefficient, right? And this is like you can plug this into an exponential and calculate the P out over the P in, right? For a distance x, right? That's minus, it's like e to the minus x over 10 alpha. So, but also you have to contend with the thickness and the length, right? So, so you have to look at the little triangle that's created here, right? And that triangle here has this angle theta is up in the corner. Then L sub I is what you want, right? You want L sub I given a value of x sub I and a value of the thickness 0.569, right? So the cosine of that is 0.569 over L sub I, right? This is opposite over hypotenuse. And so that's what that looks like. And then I don't know if that's relevant or not, the tangent there. That's also true, right? Oops. And so let's see here. And then what you have is you have them sort of stacked up against them. You got x1, x2, x3, x4, and you got x sub n, right? And the sum of the x sub I is 3.24 centimeters, right? That's another thing that we know because this is the total length. right? And then x times n is equal to 3.24. That's another way of saying that. So n is equal to 3.24 over x. And so in any case here, we can put in we can substitute some values in there. For example, cosine of theta, we can put in the cosine of 70, which is in the example that I had, it was 70 degrees. And then this gives us an individual hypotenuse. Oops, am I on screen here? Nope. L sub I, right? And so this gives us this, and then to calculate n here, we'll calculate the x value, the individual x value, or I'm sorry, yeah, I'm calling it the individual x value there, right? And so the x value comes from the tangent function, and that guy comes out to 1.56 times 10 to the minus 4. Then you just plug in the total length here. And then this gives you the number of bounces. And then you integrate these two guys, and this gives you the total length. Oops, I can't tell here. I'm off screen. The total path length in the waveguide. Okay. And then from there, we have to do the exponential math. And the exponential math is that we take this total length and this is L, right? L alpha over 10, raise 10 to that power, and you get the P in value is 0.897, right? So, I think I got this one wrong, but anyway, this was my answer. And we can also do 13 and 14, yeah. So, and then let's see here. And then the wavelength, 514 in vacuum. Oops. And divided by 1.70 gives 302 nanometers in like some organic material. And then, but the frequency is unchanged. So see if you can follow through with that. And if you get it wrong if everybody gets it wrong in the homework, then I'll drop it or something. But that's how I did it. So now somebody also wanted to see 13 and 14. Okay, so let's see about those guys. Were they the stray light problems? Let's see which ones were they. Okay, there's dispersion. So I think I might have already done this one, but let's see here. Oh yeah, here we go. So I think this is the first one that I worked through. Let's see here. There we go. Wait. And so for a grading, right? There's basically three equations that we have here. There's the grading equation, n lambda equals d sine I plus sine r. There's the dispersion, which is d phi by d lambda, right? And that's equal to n over d cosine phi. And this tells you how spread out the wavelengths are. And then there's another weird one, which has to do with the number of illuminated blazes. So so this term here, NN, is this is the order, and this is the number of blazes that are illuminated. And so that just means that you can't do spectroscopy with just two slits. You need more. If you have, if you want a resolution that will resolve 1 nanometer in 1,000, then you need to illuminate at least 1,000 lines on your grading. So little n, big N equals lambda over delta. So these are the only three equations that we have for gradings right now. And you basically just have to plug in the values that you have for the problem. So for example here, this is 1,500 grooves per centimeter. This is, so the D value comes in reciprocal. And then there's the cosine of the angle. And there's the order. And then this gives you radians per centimeter. And that's one of the keys, is to recognizing that's radians, right? And then you just do unit conversions and you get to degrees per nanometer there. All right. 41, 43, 44. Okay. So 13 and then 14. Let's see. Let's look at 14 here. Let's see here. So let's see here. 14 is going to be let's see. So basically 14, what you have to do oh, you have to solve the grading equation for D and then convert D into lines per centimeter. So so for example here, if you have, a given angle of refraction, a given D value, and you want to know the D value for these other parameters. You want to get 550 nanometer light, you want to read in first order, and the refracted angle is 31 degrees, then you just plug in theta, phi, lambda, and n, and you can solve it for D. There's 1 times 550 times 10⁻⁹ meters over sine I plus sine R, or sine theta plus sine phi. You plug in those values and you notice you've got a negative value there. That's okay. You just subtract them away. And then this is the number of centimeters per line, right? And then you just flip it over, just 1 over x it there. And that gives you 4358 lines per centimeter, which is what I got. And then you can change them around to get the other answer. Okay, so next question. Any other homework questions?
Number 4.
I think I've number 4. Okay. All right. So let's see here. Okay. Oh, black body emittance. Okay, I'm not sure. I think I did this one, but I'm not sure I recorded. Let me see here. Yeah, I'm not sure I did this one. Oh my God. This is really like mathematical soup, isn't it? Just a lot of constants in here. So, oh God. So I can't do this one right now. I'm just like, my brain is not prepared. Different question, please. Have some pity on me. My God, man. That's you, isn't it? It's you, folk.
Yes,
You
it's
requested
me.
you requested this. I know you did.
Yes, I did.
Oh my
Number
God.
4.
Could we have this
Never
Uh,
mind that this is what you assigned to us. And it said, oh, these problems
Oh,
are
oh God.
easy.
Oh God. Well, okay. You know what I would do is I would do this one in Excel actually, because there's just so many little places to go wrong. It's like, oh, it's easier to debug in a higher level language, but I'm not. Maybe I'll do it Thursday, and I think I've actually done it. I just tore it up and threw it away because I didn't like it or something.
May
I don't know.
we do
I'm
26,
sorry.
Dr. T, if possible? If possible, 26.
All right.
Or
All
please,
right. All
26.
right. All right. All right. All right. All right. Let's try 26. Let's try 26. See if I did 26. Oh yeah, I did 26. Yes. I did do 26. I did do it. And it's actually fairly easy. So hopefully it comes out that way. So let me get my share fixed up here. So basically we've got they give you the equation here, you know. So there's a way to for every laser pulse that comes out, you get a time constant for the decay, right? And the time constant for the decay minus, you know, the reciprocal time constant here, whatever you call that, the decay frequency minus the decay frequency for the blank. This gives you the absorbance, you know. That's kind of cool. It's all a temporal thing, you know. There's no light power in this equation. It's kind of trippy that way, but if you put in a pulse, right, you can measure a tau value, and so the empty cavity, this is tau 0, and this is tau, right? And so, and here I'll show you how I did it. Let's see here. So I just, the values I had were a little bit different here, right? But if you have a 22 centimeter cavity, this is L. You know, C is the speed of light. And then, you know, log of 10, 2.303. And then tau 0 and tau, right? So you basically just substitute all those values in there. There's seconds. So this is this value is in per second. This is in centimeters and centimeters. They cancel. And then per second in the numerator and per second in the denominator cancel. And so basically you get an absorbance of 2.44 times 10 to the minus 6, right? In my case, right? And the thing about this that's remarkable is that this is a very small value. You know, it's not easy to measure that directly. I've never really heard of anyone measuring an absorbance of that small of a magnitude, you know, except in this weird time domain type spectroscopy. Take that one off the homework again. So, you know, yes, I do pity you, but you know, it's not, it's like, just take that one off the homework again. Which one? The complicated, the emittance one. Oh, I can't do that. It's already done. It's already done. I have to be mean. I can't take it off. Saudi. Okay, so any more requests?
Can you just talk about the
Yes?
lab reports at some point, Dr. Terrell?
Oh, sure. Oh, yeah.
I mean, not today. I don't
So,
think we have time, but yeah, just at some point.
okay, all right. Well, there's one thing I can say is that do them because they are coming. And for those of you who've been turning them in, just look at the comments because sometimes I don't grade them and I say, hey, can you fix this? So I can give you full points, you know? But if I get it and it's like the last week or something, I'm not going to do that, you know? Because I need to get the grades done, you know? So anyway, so if you do it now, then I can give you a chance to get a better grade. But if you do it later, then I can't really do that. So also for the Raman, there's some questions in there. Let me see if I can find my Raman questions here. Let's see here. You'll see here, I should be sharing this screen, right? There we go. There were 3 crystal violets that I returned and 1 Raman that I returned. And they're basically just like the crystal violets, you just got to look at them again. And, you know, there's some wacky answers. And I thought, you know, I don't want to take off points for, you know, magnitude errors. And then the short report here, I'll show you the questions and answers there. So let's see here. Let's do files. And then lab. And then lab manual.
Dr. Terrell, is the crystal violet and UV vis lab the same thing?
No,
Because we did 4 labs, right?
they're right. Yeah, we did crystal violet fluorescence, Raman, and HPLC.
So we don't have to do UV vis?
No, we're not doing UV vis.
Oh, okay.
We're not doing that in the lab. Yeah, we sort of did it in the homework, but we're not doing it in the lab. So let's see here. Then the Raman knob, huh? There we go. Page 52. Control click, maybe. Page 52. This is going to put me, oops. Come on. Oh, there we go. There we go. There's the Raman one. So basically the way to do the Raman is to do the Excel like I show you, and then answer the questions based on then you basically answer these 3 questions. You know, calculate the scattered light where you would see 3,000 wave numbers. What common solvent peak cannot be used in FTIR but can be used in Raman? That would be water, because in FTIR it's so strong that it overwhelms everything. And then you can basically what you need to do is calculate the new bar for 785 and the new bar for 787, and then take the difference in those, and that will tell you the effective bandwidth, right? It's like 64 wave numbers or something, or 32 wave numbers, something like that. But it's only 2 nanometers at 785. So basically, it's saying that Raman is a little bit lower resolution. So do these questions.
Professor,
Alrighty, guys. Yes.
would you
yes,
want us to
yes, sir,
answer
yes,
those
sir.
questions on like a Word document and then post our graphs in there, or just put them in the Excel?
You can just put them in the Excel. That's a little bit easier for me if it's all in one thing.
Okay, sounds good.
Or you could put them in a Word. It's fine. Either way, you could write them in crayon on a napkin and take a picture of them from 10 feet away, where there's a bunch of weird stuff, random things in the picture, and takes me quite a while to focus in on the and mentally decrumple the napkin that you wrote it on.
Right, but I wouldn't want to do that to you.
Are you sure? Alrighty. Thank you very much. I better go now before I get fired. I will see everybody in lab and have a good time. Email me, come to office hours, do all that good stuff, please.
Thank you, Dr. T.
Thanks, Dr. Terrell. See you.
Bye.
Thank you,
Sure.
Dr.
Thank
Terrell.
you. Talk to you soon. Bye-bye. Bye-bye.